Look up at the night sky, and you'll see something astonishing. Not just the vastness of space, but a hidden language of patterns, repeating itself in ways that feel strangely familiar. The swirling arms of a distant galaxy, for instance, don't just spin in isolation. They twist and curve with the same elegant motion as a hurricane over the ocean, or the unfurling branches of an ancient tree. How is it possible that the grandest structures in the universe mirror the smallest details of our world? This isn't just coincidence, it's a clue, a whisper from the cosmos that everything, from the tiniest leaf to the largest galaxy, is woven together by invisible threads of harmony. Welcome to the mystery of cosmic reflections, where the universe reveals itself not as a chaotic void, but as a grand tapestry of repeating shapes, rhythms, and symmetries, a code written into the fabric of reality itself. Think about the last time you saw a snowflake. Its delicate, branching arms are a masterpiece of fractal geometry, a pattern that repeats itself at smaller and smaller scales, creating infinite complexity from simple rules. Now, imagine that same pattern etched into the veins of a leaf, the tributaries of a river, even the lightning bolts that split the sky. These aren't just random similarities. They're echoes of a deeper truth. The universe has a favorite way of building things, a universal blueprint that shows up again and again, from the quantum realm to the cosmic web. What if I told you that the same forces shaping the swirl of your coffee also sculpt the orbits of planets, or that the vibrations of atoms might dance to the same rhythm as the spinning of stars? This is the journey we're about to take, one that will unravel the hidden connections between the world we know and the cosmos that cradles it. From the spirals of seashells to the orbits of galaxies, nature's patterns are more than just beautiful. They're a window into the laws that govern everything. Over the course of this exploration, we'll uncover how fractal geometry ties the branching of trees to the structure of the universe itself. We'll see how quantum symmetries might hold the key to understanding the balance of forces that keep stars shining and planets spinning. And most importantly, we'll discover what these cosmic reflections tell us about our place in this grand design. Because if the universe truly mirrors the patterns of our world, then perhaps we're not just observers of its beauty, we're part of its story. So let's begin this journey together and unlock the secrets written in the stars, the seas, and even the palm of your hand. The universe has a favorite way of organizing itself, not in straight lines or perfect circles, but in intricate, repeating cascades of shapes that look eerily similar whether you're zoomed in or out. This is the magic of fractals, patterns that echo themselves across scales, appearing in the veins of a leaf just as vividly as they do in the sprawling arms of a galaxy. The mathematician Benoit Mandelbrot first gave these patterns a name, revealing that what seemed like chaos, the jagged edge of a coastline, the branching of a river delta, even the uneven distribution of galaxies, was actually a hidden order. Take a moment to study a fern leaf. Notice how each tiny frond mirrors the shape of the whole branch, and how that branch mirrors the entire plant. Now pull back further. A bolt of lightning fractures the sky with the same branching elegance. And further still, the tendrils of gas in a distant nebula swirl with that same familiar rhythm. What's astonishing isn't just that these patterns repeat, but why they repeat. Nature isn't copying itself for beauty's sake. It's following a set of deep mathematical rules that govern growth, movement, and even the flow of energy. When wind carves a mountain or water erodes a canyon, it doesn't follow a blueprint. It obeys the path of least resistance, creating fractal shapes naturally. The same principle applies to the cosmos. The distribution of matter in the universe isn't random. It clusters in ways that resemble the branching of roots or the foam of ocean waves. Scientists call this the cosmic web, a vast network of filaments and voids that looks uncannily like a neural network in the human brain. This isn't just poetic symmetry, it's a clue. Fractals suggest that the universe operates on a set of universal algorithms, simple rules that manifest in wildly different contexts. A single equation can generate the infinite complexity of the Mandelbrot set, just as a single law of physics might shape everything from the spin of electrons to the orbits of planets. So the next time you see a snowflake, pause and consider, its design isn't just a fleeting wonder. It's a whisper of the same forces that sculpted the galaxies, a reminder that the universe loves to repeat its favorite patterns, and that we're here to decipher them. There's a number so precise, so universal, that it appears in the petals of a rose, the curve of a breaking wave, and even the grand design of galaxies. It's called the Golden Ratio, approximately 1.618, a mathematical constant known as phi that seems to whisper through the fabric of reality. Picture the spiral of a nautilus shell, each chamber growing wider by this exact ratio, creating a curve so perfect it feels almost intentional. Now, look deeper. That same spiral unfolds in the swirling arms of a hurricane, the arrangement of seeds in a sunflower, and even the vast structure of our own Milky Way. How can a single number bridge the gap between the microscopic and the cosmic? The secret lies in the Fibonacci sequence, a series of numbers where each one is the sum of the two before it, 0, 1, 1, 2, 3, 5, 8, and so on. Divide any number in this sequence by its predecessor, and the result inches closer and closer to phi. This isn't just a neat math trick. It's a growth pattern so efficient that nature adopts it everywhere. Trees branch out following Fibonacci numbers to maximize sunlight, while galaxies spin in logarithmic spirals that mirror the same proportions. Even the human body echoes this ratio. The length of your forearm to your hand, or the spacing of your facial features, often align with phi. But here's the real mystery. Is this harmony just a happy accident, or does it hint at something deeper? Some scientists argue that the golden ratio emerges naturally from the laws of physics and biology, a mathematical solution to the problem of packing, growing, or moving efficiently. Others wonder if it's a glimpse of a fundamental order, a shared blueprint woven into the universe itself. When we see the same spiral in a seashell and a galaxy, are we witnessing the universe's favorite way of building beauty? This brings us to symmetry, another cosmic signature that might hold the key. If the golden ratio is nature's favorite number, then symmetry could be its most cherished shape. From the hexagonal perfection of a snowflake to the mirrored wings of a butterfly, balance seems to be written into the code of existence. And just as phi appears across scales, symmetry reveals itself in the quantum realm and the vast structure of spacetime. Could these patterns be clues to a deeper unity, a hidden language that ties everything together? One thing is certain: the universe loves to repeat its most elegant designs, inviting us to look closer and listen to the whispers of its grand design. Symmetry surrounds us not just as a pleasing aesthetic, but as a fundamental law woven into the very structure of reality. Consider the perfect hexagonal symmetry of a snowflake, each icy branch mirroring the others with mathematical precision. This isn't just frozen artistry. It's a direct result of how water molecules arrange themselves under the rules of chemistry and physics. Now, zoom out to the crystalline landscapes of distant planets, where mineral structures form identical geometric patterns under extreme pressures and temperatures. The same forces that shape a snowflake's delicate arms also sculpt the jagged cliffs of Pluto's frozen plains. What does this tell us? Symmetry isn't just a quirk of nature, it's a universal language, a silent code that governs everything from the smallest atomic bonds to the grandest celestial designs. The physicist Emmy Noether unlocked one of symmetry's greatest secrets. Every symmetrical property in nature corresponds to a conserved law of physics. The rotational symmetry of a planet's orbit, for instance, ties directly to the conservation of angular momentum. Why spinning objects keep their motion unless acted upon? This profound connection reveals symmetry not as decoration, but as the backbone of physical law. A butterfly's wings, painted with mirrored patterns, aren't just beautiful by chance. Their symmetry emerges from the same genetic algorithms that guide cellular growth. Even the spiral arms of galaxies, though vast and turbulent, obey symmetrical principles of gravitational balance. Yet for all its perfection, symmetry has a counterpoint, asymmetry, the cosmic wildcard that breathes dynamism into the universe. Supernovae explode in chaotic, lopsided bursts, scattering heavy elements asymmetrically across space, yet without these violent irregularities, life as we know it wouldn't exist. The human heart rests slightly off-center in our chests, a reminder that balance doesn't always mean mirror images. Perhaps asymmetry isn't symmetry's opposite, but its partner, a necessary disruption that sparks change, diversity, and evolution. So when we gaze at the night sky or examine a leaf's veins, we're not just seeing order or chaos, but a dialogue between the two, a dance of patterns that shape the universe's endless creativity. Chaos and order, these two forces seem like opposites, locked in an eternal struggle. But look closer and you'll find their partners, dancing together to shape the universe in ways both unpredictable and breathtakingly precise. Take Jupiter's great red spot, a swirling tempest twice the size of Earth that has raged for centuries. On the surface, it's pure chaos, a hurricane of gas spinning at hundreds of miles per hour. Yet hidden within that turbulence is a strange stability, a self-renewing order that keeps the storm alive. Meanwhile, on our own planet, weather systems come and go in days, their paths so sensitive to tiny changes that forecasting them feels like reading tea leaves. Why does one world's chaos settle into longevity while another's remains stubbornly wild? The answer lies in entropy, the universe's tendency toward disorder, and the surprising ways complexity emerges from it. Picture an asteroid belt, thousands of rocky fragments clattering together in what seems like random motion. Over time, gravity sculpts this chaos into patterns, nudging some asteroids into stable orbits while ejecting others into the void. Even in the apparent randomness, there's a hidden rhythm. The same principle applies to DNA, where the double helix's elegant structure arises from the chaotic dance of molecules obeying simple chemical rules. Chaos isn't the absence of order, it's the raw material from which order is born. This brings us to the edge of chaos, a delicate balance where systems are neither too rigid nor too disordered. Think of it as nature's sweet spot where creativity thrives. A forest fire might seem purely destructive, but it clears space for new growth. Earth's tectonic plates grind and fracture unpredictably, yet their movement builds mountains and carves continents. Even the human brain operates at this edge, with neurons firing in patterns that blend stability and spontaneity to generate ideas. Now, consider star formation, a process that begins in the densest, most turbulent clouds of gas. These cosmic nurseries are anything but calm. They're seething with collisions and shock waves. Yet within that chaos, pockets of gas collapse under their own weight, spinning into ordered disks that ignite into stars. Turbulence, it turns out, isn't just destruction, it's a sculptor, shaping the universe's grandest structures. So the next time you see disorder in nature, whether in a stormy sky or a bustling city, remember, chaos might just be the universe's way of making something new. Deep in the swirling clouds of a stellar nursery, where gravity pulls gas and dust into dense knots, a star begins its life, not unlike the way a single cell divides and multiplies in the hidden currents of a living organism. At first glance, these processes seem worlds apart, separated by unimaginable scales. But look closer, and the similarities become startling. Hubble's breathtaking images of protoplanetary disks, those glowing, pancake-shaped rings of material around young stars, reveal spiraling arms and concentric rings that could easily be mistaken for the microscopic view of a cell undergoing mitosis. Both systems rely on an invisible scaffolding. For stars, it's the gravitational forces that sculpt collapsing gas. For cells, it's the intricate dance of microtubules pulling chromosomes apart. Parallels go even deeper. Just as a star forms when a dense core gathers enough mass to ignite nuclear fusion, a cell's division is triggered by precise thresholds of chemical signals and energy. In both cases, rotation plays a crucial role. Protoplanetary disks spin as they flatten, their material spiraling inward to feed the growing star, mirroring the way chromosomes align and separate along the spinning axis of a dividing cell. Even the turbulence within these systems follows similar rules. The chaotic motions of gas in a stellar nursery echo the Brownian motion of molecules within a cell, where randomness and order coexist to drive creation. This raises a profound question. Could the same universal principles be guiding both the birth of stars and the rhythm of life? Scientists studying complexity theory think so. They've found that networks, whether they're the gravitational bonds between particles in a nebula or the signaling pathways in a cellular organism, tend to self-organize in strikingly similar ways. Filaments of gas threading through star-forming regions resemble the cytoskeleton of a cell, both acting as highways for transporting essential materials. Even the way stars cluster into galaxies mirrors how cells organize into tissues, drawn together by forces we're only beginning to understand. Perhaps this isn't just coincidence, but a hint of something deeper. The universe seems to favor certain patterns, whether it's building a star or a strand of DNA. And if that's true, then the boundary between the cosmic and the microscopic might be far more fluid than we ever imagined. After all, the elements forged in stellar furnaces, carbon, oxygen, nitrogen, are the very same ones that weave together to form our cells. We're not just observers of the cosmos, we're made from its stardust, bound by the same elegant rules that shape galaxies and govern life. So the next time you see an image of a distant nebula or peer into a microscope, remember, you might be looking at two versions of the same cosmic story. Inside the human brain, nearly 100 billion neurons weave together in an intricate web, firing signals across trillions of connections, a network so vast and efficient, it shapes every thought, memory, and dream. Now step back, way back into the depths of space, where another unimaginably vast web stretches across the cosmos. The filaments of dark matter, threading through the universe like ghostly scaffolding, with galaxies clustering at their intersections like stars caught in a spider's silk. At first glance, these two networks, one inside our skulls, the other spanning billions of light years, couldn't seem more different. But look closer, and the similarities become uncanny. Both systems organize around dense hubs with sprawling tendrils between them, optimizing the flow of something essential. For the brain, its electrical impulses; for the cosmos, its gravity's invisible pull. Scientists mapping the cosmic web have noticed something extraordinary. The distribution of galaxies mirrors the way neurons cluster in a brain's neural network, with both systems following what's known as a small world architecture, a design that balances local clustering with long-range connections. Just as neurons communicate across distant regions of the brain through key relay points, galaxies influence one another through the gravitational bridges of dark matter, exchanging energy and matter across unfathomable distances. Even more striking, when researchers simulated the growth of these cosmic filaments using supercomputers, the results resembled time-lapse footage of a living neural network forming, as if the universe and the mind were built from the same blueprint. But perhaps the most surprising comparison comes from an organism with no brain at all, slime mold. In experiments, scientists observed how these single-celled creatures, when presented with food sources arranged like cities, construct efficient nutrient transport networks that eerily resemble human-designed systems like Tokyo's subway or the Internet's fiber optic backbone. The mold doesn't plan or calculate, it simply follows chemical gradients, yet consistently finds the most optimal pathways. Now, apply that to the cosmic web. Dark matter, invisible and mysterious, seems to solve the same problem on a galactic scale, guiding matter into filaments that minimize energy loss over cosmic distances. Could these eerily similar networks, slime molds, city plans, brains, and galaxies all be obeying a hidden set of universal optimization rules? That's where dark matter's greatest mystery lies. We still don't know what it is, only that its gravitational influence shapes everything. Yet its behavior, how it clumps, flows, and connects the universe, might hold clues to a deeper pattern, one that echoes in systems large and small. Some theorists speculate that dark matter's structure isn't random but computational, acting as a kind of cosmic processor that helps the universe solve the problem of organizing matter efficiently. If that's true, then the web binding the galaxies might be more than a passive scaffold. It could be a dynamic, evolving network, humming with the same invisible logic that guides the growth of roots, the spread of cities, and even the firing of our own synapses. And if we can decode that logic, we might finally understand why the universe builds itself this way, from the smallest cell to the largest supercluster. Imagine an enormous tree, its roots spreading unseen beneath the soil, invisible to the eye yet holding the entire structure upright. Now picture a galaxy, a swirling disk of stars, gas, and dust, anchored by something just as hidden, dark matter. This mysterious substance doesn't shine, reflect, or absorb light. Yet its gravitational pull is the hidden hand shaping every galaxy, every cluster, every filament of the cosmic web. Without it, the universe as we know it would fly apart. Stars on the outer edges of spiral galaxies, like our Milky Way, orbit so fast that they should be flung into the void. But they aren't, because dark matter's invisible grip holds them in place, just as roots stabilize a tree against the wind. The astronomer Vera Rubin first uncovered this cosmic secret in the 1970s, meticulously measuring the rotation speeds of stars in distant galaxies. What she found defied expectations. Stars far from the galactic center were moving just as fast as those near it, a phenomenon that shouldn't be possible under Newton's laws unless some unseen mass was holding everything together. Her work revealed that visible matter, the stars, planets, and glowing gas we see, makes up less than 20% of a galaxy's total mass. The rest is dark matter, an enigmatic substance that interacts with gravity but remains utterly transparent to light. Here's where the metaphor deepens. Just as roots draw nutrients from the soil to nourish a tree's growth, dark matter's gravitational pull gathers ordinary matter into the dense pockets where galaxies are born. Simulations of the early universe show how dark matter's subtle clumps acted like gravitational wells, drawing in hydrogen and helium until the pressure sparked star formation. Over billions of years, these seeds grew into the majestic spirals and ellipticals we observe today. Yet dark matter doesn't just build galaxies, it connects them. Vast filaments of this invisible material stretch across the cosmos, forming a scaffolding where galaxies cluster like fruit on a vine. But dark matter behaves differently from the matter we know. While stars and gas collide, swirl, and light up the sky, dark matter passes through itself like a ghost, leaving no trail. It doesn't crumple or compress. It forms diffuse halos that extend far beyond a galaxy's visible edge. This strange quality raises a tantalizing question. If dark matter is the cosmic soil nurturing galactic structures, what does that make its elusive counterpart, dark energy? While dark matter pulls the universe together, dark energy seems to do the opposite, pushing space itself apart in a mysterious cosmic tug of war. Together, these invisible forces sculpt the universe on the grandest scales, hidden architects in a drama we've only just begun to understand. If dark matter is the unseen root system of the cosmos, then dark energy is the mysterious wind pushing the branches apart, an invisible force stretching space itself faster and faster, as if the universe is breathing outward. Picture a forest floor after rain where fungi erupt overnight in sprawling networks. Their thread-like hyphae spread in all directions, not by chasing sunlight like plants, but by responding to some hidden imperative of growth. Dark energy behaves similarly, not pulling or clustering like gravity, but permeating empty space with a relentless pressure that drives galaxies apart. The more the universe expands, the more dark energy seems to emerge, creating a feedback loop that echoes the exponential spread of life in a nutrient-rich environment. Einstein first hinted at this phenomenon with his cosmological constant, a mathematical term he added to his equations to keep the universe static, later calling it his greatest blunder when Edwin Hubble discovered the cosmos was actually expanding. But modern observations of distant supernova revealed something even stranger. That expansion isn't just continuing, it's accelerating. Dark energy, making up nearly 70% of the universe's total energy, appears to be the culprit. Think of it like blowing up a balloon with invisible ink. You can't see what's stretching the rubber, but you watch as dots drawn on its surface galaxies move farther apart, and the faster you inflate it, the quicker those dots recede. Yet here's the haunting question. Is dark energy truly constant, or could it pulse like a cosmic heartbeat? Some theories suggest vacuum energy, the seething quantum particles that pop in and out of existence in empty space, might fuel this expansion. Others propose dark energy's strength could change over time, meaning the universe's fate might swing between endless expansion or a dramatic collapse. This uncertainty mirrors the rhythms of nature, where growth spurts and contractions shape everything from heartbeat intervals to the cyclical spread of forest fires. And just as these natural cycles give direction to time, a tree's rings marking years, a river carving deeper canyons with each flood, dark energy may hold the key to time's arrow on a cosmic scale. Entropy dictates that disorder increases over time, but dark energy's push against gravity's pull could determine whether the universe ends in cold dispersion or a dramatic crunch. The irony is profound. The same force driving galaxies apart might also be writing the final chapter of time itself. So when we look up at the night sky, we're not just seeing distant stars, we're witnessing the invisible tug of war that shapes existence, from the smallest fungal tendril to the fate of all things. Time moves in one direction, or at least that's how we experience it. A shattered glass doesn't reassemble. A river never flows backward. This irreversible march is called entropy, the universe's tendency toward disorder, and it's woven into the fabric of reality itself. But here's the paradox. While entropy pulls everything apart, life, and even the cosmos seems to build itself up, growing more complex over time. Picture the fossil record, layer after layer of ancient life, each stratum revealing organisms adapting, diversifying, defying decay through evolution. Now compare that to the cosmic microwave background, the afterglow of the Big Bang. Its faint ripples are like a fossilized snapshot of the infant universe, a time when matter was nearly uniform without galaxies or stars. Over billions of years, gravity sculpted that smoothness into the intricate web of galaxies we see today. How can disorder and complexity coexist? Stephen Hawking once pondered this puzzle, calling time's asymmetry the most mysterious thing about the universe. Entropy dictates that systems move toward chaos, yet evolution, whether biological or cosmic, creates structure from DNA to spiral galaxies. The key lies in energy flow. A star, for instance, burns hydrogen into helium, releasing heat and light while increasing entropy overall. But within that fiery furnace, heavier elements like carbon and oxygen form ingredients for planets and life. Similarly, Earth absorbs the sun's energy, allowing plants to grow, animals to thrive, and ecosystems to diversify, even as the larger universe trends toward disorder. It's as if the cosmos has found a way to carve out pockets of complexity amid the chaos, like eddies in a rushing river. This raises a tantalizing possibility. Could universes themselves evolve? Some cosmologists speculate that black holes might act as cosmic seeds, birthing new universes with slightly tweaked physical constants, a form of natural selection on a grand scale. Others imagine cyclical models where universes expand, collapse, and rebound in endless iterations, each cycle inheriting traces of the last. Ancient Hindu cosmology spoke of cosmic cycles lasting trillions of years, while modern theories like conformal cyclic cosmology suggest that the distant future of one universe could become the Big Bang of another. Whether these ideas hold or not, they echo a profound truth. Time isn't just a ticking clock. It's a storyteller weaving tales of decay and renewal, entropy and emergence, all written into the stars and the cells of every living thing. Everywhere we look, the universe moves in cycles, great cosmic rhythms that pulse through space and time like a heartbeat. Take the humble Cepheid variable star, a celestial beacon that brightens and dims with clockwork precision. These stars expand and contract, their outer layers breathing in and out as internal pressures battle gravity. Their rhythmic flickering isn't just beautiful, it's a cosmic metronome, helping astronomers measure vast distances across the void. Now zoom in closer to our own solar system, where planets trace elliptical loops around the sun, locked in orbits so reliable we can predict their positions millennia in advance. Even Earth's dance isn't just a simple circle. It's a spiral through space, carrying us around the galaxy once every 230 million years. But cycles aren't confined to the heavens. They echo through our own bodies, woven into the fabric of life itself. Circadian rhythms, the 24-hour cycles governing sleep, hormone release, even metabolism, are so fundamental that disrupting them can unravel our health. These biological clocks are ancient, older than humanity itself, synchronized by sunlight like celestial conductors, keeping time for every living thing. Some scientists believe this connection runs deeper, that the same gravitational forces tugging at the tides might have subtly shaped life's earliest rhythms. After all, the moon's phases guided our ancestors long before clocks existed, tying human routines to the cosmos in ways we're only beginning to understand. Yet not all cultures see time as a straight line rushing from past to future. Many indigenous cosmologies, from the Lakota to the Aboriginal Australians, envision time as a great circle, a wheel where seasons, stories, and generations return like constellations reappearing in the night sky. In these traditions, the present isn't just a point on a timeline. It's a crossroads where ancestors and descendants meet, where history isn't just remembered but relived. This cyclical view mirrors the cosmos itself, where nothing truly ends, it transforms. When a massive star explodes as a supernova, it doesn't vanish. It scatters its guts across space, seeding clouds of gas with carbon, iron, gold, the very elements that will one day coalesce into new stars, planets, perhaps even life. That's the universe's quiet secret. It's a master recycler. The oxygen in your lungs, the calcium in your bones, even the iron in your blood were forged in stellar furnaces and scattered by cataclysmic explosions billions of years ago. We're made from star stuff, as Carl Sagan famously said, but more than that, we're made from the remains of stars that died so others could be born. This endless exchange turns the cosmos into something more than a machine. It becomes a living, self-renewing organism, breathing in dust and breathing out light. The question isn't whether the universe has a rhythm, it's whether we're listening closely enough to hear its song. In the dense forests of the Amazon or the icy expanses of Antarctica, Earth doesn't just host life, it behaves like a living organism itself. This is the heart of the Gaia hypothesis, proposed by James Lovelock and Lynn Margulies in the 1970s. They saw our planet not as a passive rock covered in organisms, but as a self-regulating system where life and environment co-evolve in a delicate dance. Oceans regulate salinity, forests modulate atmospheric gases, and microbes stabilize soil, all without a central director, as if the biosphere itself were an immense, breathing entity. Now stretch that idea across the cosmos. If a single planet can function like a living system, what stops us from imagining galaxies, or even the universe, doing the same? Consider the way galaxy clusters evolve. They aren't static islands in space. They grow, merge, and recycle matter in ways that eerily resemble biological metabolism. Giant elliptical galaxies, for instance, often sit at the centers of clusters like hearts in a circulatory system. They're supermassive black holes acting as cosmic pacers, regulating energy flow. Surrounding them, hot gas, the clusters, blood, shuttles elements forged in stellar explosions to new regions, where they'll eventually form new stars and planets. Even dark energy, that mysterious force accelerating the universe's expansion, could be seen as part of this cosmic metabolism. Just as mitochondria in cells convert nutrients into usable energy, dark energy might be the universe's way of processing space-time itself, transforming the vacuum into the fuel for expansion. Lovelock and Margulies faced skepticism for their Gaia theory, dismissed by some as poetic metaphor rather than hard science. Yet modern research reveals just how tightly Earth systems are intertwined. The sulfur compounds released by ocean algae, for example, seed clouds that reflect sunlight, cooling the planet. Similarly, astronomers now study galactic feedback loops, where dying stars inject energy and heavy elements back into their surroundings, triggering or stifling new star formation. These aren't just isolated processes, they're part of a vast, self-adjusting network, which raises a provocative thought. Could the universe possess a kind of quantum metabolism? At the smallest scales, particles pop in and out of existence, trading energy in fleeting interactions. Some theories suggest these quantum fluctuations might influence gravity itself, subtly shaping how galaxies cluster. It's as if the fabric of spacetime is alive with invisible activity, a hum of potentiality that underlies everything. From the self-organizing patterns of slime molds to the large-scale structure of the cosmos, complexity seems to emerge from simple rules, rules that might operate across every scale, binding the quantum to the cosmic. If that's true, then the universe isn't just a place where life exists. In a very real sense, it might be alive. Einstein called it spooky action at a distance, a phenomenon so strange it made even the greatest scientific minds uneasy. Quantum entanglement, the bizarre connection between particles that instantly influences one another no matter how far apart they are. defies everything we know about space and time. Imagine two coins flipped simultaneously on opposite sides of the galaxy, yet always landing on matching faces. That's entanglement in action, a cosmic mirroring where the state of one particle determines its partner's state instantaneously, faster than light could ever travel between them. For Einstein, this wasn't just puzzling. It was an outright rejection of the orderly universe he believed in. Yet today, experiments confirm entanglement is real, leaving us with a profound question. If particles can communicate across vast distances without any apparent signal, what does that say about the fabric of reality itself? This eerie connection isn't confined to the quantum realm. Beneath our feet, sprawling fungal networks known as the Wood Wide Web link trees in a silent, symbiotic conversation. When a Douglas fir is attacked by beetles, it releases chemical signals through these fungal threads, warning neighboring trees to bolster their defenses. The forest behaves like a single organism, with individual trees acting as entangled particles in a vast, living system. Just as entangled photons remain mysteriously linked, trees separated by miles stay in sync through invisible pathways, nature's own version of quantum weirdness playing out on a scale we can see and touch. Could these parallels hint at something deeper? Some physicists speculate that entanglement might be a clue to the universe's true nature, not as a collection of separate objects, but as an interconnected hologram where every part contains information about the whole. In this view, the cosmos operates more like a neural network than a machine, with entanglement acting as the threads stitching reality together. A single particle's behavior in a lab on Earth might ripple through the quantum fabric, influencing its entangled twin near a distant star, all because the universe is fundamentally indivisible. This isn't just philosophy. Researchers are already harnessing entanglement to build unhackable quantum communication networks and computers that solve problems in seconds which would take conventional machines millennia. Yet the most startling implication isn't technological, it's existential. If entanglement binds the universe at its core, then separation might be an illusion, and every star, every leaf, every atom could be part of a grander, unseen unity. The cosmos isn't just reflecting patterns, it might be whispering that everything, from the smallest particle to the largest galaxy, is far more connected than we ever imagined. What if everything we see, the stars, the planets, even our own hands, isn't truly three-dimensional, but a kind of cosmic illusion? This mind-bending idea lies at the heart of the holographic principle, a theory suggesting that all the information in our universe might be encoded on a two-dimensional surface, like a projector casting a 3D movie onto a flat screen. Think of a hologram on a credit card. Tilt it, and you see depth, shadows, even motion, yet it's all contained in a thin, flat layer. The universe, some physicists argue, could work the same way, with the fabric of reality itself acting as a vast, shimmering projection from some hidden boundary we can't yet perceive. The roots of this idea trace back to an unexpected place: black holes. When matter falls into a black hole, it vanishes from our observable universe, seemingly erasing information, a direct violation of quantum mechanics, which states that information can never be lost. This contradiction, known as the black hole information paradox, haunted physicists for decades until a breakthrough emerged. Researchers calculated that all the data swallowed by a black hole isn't destroyed. It's imprinted on the event horizon, the point of no return, like a celestial fingerprint. Over time, this information could theoretically leak back out through Hawking radiation, a slow evaporation of particles from the black hole's edge. But here's the twist: the event horizon is a two-dimensional surface. If a black hole's entire contents can be encoded there, could the same be true for the universe? Nature already gives us a clue in the spiral of DNA. Those twisting double strands contain all the instructions needed to build a three-dimensional organism: eyes, bones, nerves, yet the code itself is linear, written in a sequence of base pairs. Just as DNA's one-dimensional sequence unfolds into the complexity of life, the holographic principle suggests space-time might emerge from underlying data written on a flat cosmic canvas. String theorists like Leonard Susskind and Gerard T. Hooft took this further, proposing that our entire universe could be a holographic projection from a distant, two-dimensional boundary, with every particle, every force, every galaxy arising from interactions on that surface. But how would such a projection work? Imagine dipping your finger into a still pond. Ripples spread outward, their patterns determined by the shape of your touch. Now picture the universe as those ripples, with the finger being data vibrating on some far-off membrane. Even gravity, which bends space-time itself, might not be a fundamental force in this view, just an emergent effect, like the way temperature arises from the motion of countless molecules. This leads us to sound, another hidden architect of form. Just as holography hints that reality might be written in vibrations on a boundary, sound waves shape the physical world in astonishing ways. Cymatics experiments reveal how sand or water on a vibrating plate arranges itself into intricate geometric patterns, echoing the spiral of galaxies or the symmetry of flowers. Tibetan singing bowls, when filled with water and struck, create dancing droplets that seem to defy gravity, their motion choreographed by unseen acoustic forces. If the universe is indeed a hologram, could sound, or some deeper quantum vibration, be the language in which it's written? The boundary between science and poetry blurs here as we glimpse a cosmos where information, resonance, and form intertwine in ways we're only beginning to decipher. Pour sand onto a metal plate, hook it up to a speaker, and play a single, pure tone. What happens next feels like witnessing magic. The grains don't just tremble, they organize themselves into intricate geometric patterns, stars, spirals, hexagons, as if guided by an invisible hand. These are Chladni figures, named after the 18th century scientist who first mapped how sound shapes matter. At certain frequencies, the plate vibrates in standing waves, creating nodes where the sand collects and antinodes where it's flung away. The result, a snapshot of sound made visible, a frozen moment where frequency becomes form. But here's what's truly astonishing: these patterns aren't random. They mirror the same symmetry found in snowflakes, the petals of a daisy, even the hexagonal storm raging at Saturn's North Pole, a six-sided vortex larger than Earth, spinning in perfect harmony with the planet's rotation. This isn't just coincidence. Pythagoras, over 2,000 years ago, spoke of the music of the spheres, the idea that celestial bodies move in resonant harmony, their orbits creating a cosmic symphony. Though his math was poetic, modern science reveals he wasn't entirely wrong. Take Bode's law, an empirical rule describing the spacing of planets in our solar system. While not a perfect fit, it hints at orbital resonances, gravitational rhythms where planets tug on one another in repeating cycles, like pendulums synchronizing over time. Jupiter's moons, for instance, dance in precise ratios. For every orbit Ganymede completes, Europa circles twice and Io 4 times. These resonances sculpt stable pathways, preventing chaotic collisions and creating a kind of gravitational music. Now zoom out further. The universe hums with vibrations we're only beginning to detect. Gravitational waves, ripples in space-time from colliding black holes, carry frequencies, much like sound waves carry pitch. When LIGO first recorded these waves in 2015, it wasn't just proof of Einstein's predictions. It was a glimpse of space-time itself vibrating like a drumhead. Could these waves, these cosmic tones, play a role in shaping the large-scale structure of the universe? Some theorists speculate that primordial vibrations in the early cosmos might have seeded the distribution of galaxies, much like Chladni figures arrange sand into patterns. Even the cosmic microwave background, the afterglow of the Big Bang, shows faint temperature variations, imprints of pressure waves that once reverberated through the infant universe. So the next time you hear a musical note or feel the bass thump in your chest, remember, you're not just sensing sound, you're witnessing a force that sculpts sand into symmetry, guides planets into harmony, and might even weave the fabric of reality itself. The universe, it seems, doesn't just have a favorite shape, it has a favorite song. On September 14, 2015, a ripple passed through Earth so faint that it shifted the fabric of space itself by less than 1/10,000th the width of a proton. Yet that minuscule tremor detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, marked one of humanity's greatest scientific achievements, the first direct observation of gravitational waves. Their source, a pair of black holes, each about 30 times the mass of our Sun, spiraling toward one another 1.3 billion light-years away. As they merged in a cataclysmic collision, they unleashed a burst of energy equivalent to 3 solar masses converted into pure gravitational waves, warping space-time like a pebble dropped into a cosmic pond. Picture that pebble hitting the water's surface. Concentric rings expand outward, growing fainter but never truly disappearing, carrying the memory of impact across the pond. Gravitational waves behave similarly, stretching and compressing spacetime itself as they travel at light speed through the universe. But unlike water ripples, these waves don't need a medium, they're undulations in the very fabric of reality, predicted by Einstein a century before LIGO discovery. What's astonishing isn't just their existence, but what they reveal about the universe's most violent events. When black holes merge, their gravitational waves carry a unique chirp, a rising frequency that spikes abruptly at the moment of collision, imprinting details about their masses, spins, and even the shape of spacetime near the event horizon. Yet these waves aren't just messengers of destruction, they are also echoes of creation. The same physics that governs colliding black holes may hold clues to the universe's first moments. Cosmologists speculate that primordial gravitational waves, generated during the Big Bang's inflationary period, still ripple through the cosmos today. These ancient vibrations would carry a distinctive pattern, like a fingerprint of the universe's explosive birth. Detecting them could confirm theories about how space expanded faster than light in the first fraction of a second, seeding the structures we see today. This brings us to sound, not in the conventional sense, but as a metaphor for the universe's earliest rhythms. In the dense plasma of the infant cosmos, pressure waves sloshed back and forth, creating peaks and troughs in matter density. Over billions of years, those peaks became galaxies, while the troughs evolved into vast cosmic voids. Remarkably, we can still hear these primordial vibrations in the cosmic microwave background, the afterglow of the Big Bang. Its faint temperature variations form a harmonic spectrum, akin to musical notes frozen in time. Some researchers have even translated these patterns into audible sound, a deep, resonant hum that's been called the universe's first cry. So when LIGO lasers trembled in 2015, they didn't just detect a distant collision. They tuned us into a cosmic symphony that's been playing since the dawn of time, one where black holes drum the bass, neutron stars chime like cymbals, and the Big Bang itself lingers as a fading overture. The universe, it seems, isn't just something we see. It's something we might one day learn to listen to in its entirety. The cosmic microwave background is the oldest photograph in existence, a snapshot of the universe when it was just 380,000 years old, a cosmic infant taking its first breath of light. Imagine peeling back the layers of time like tree rings, each one marking a chapter in the universe's growth, until you reach the very center, this faint, crackling glow, the afterglow of the Big Bang itself. Stretching across the entire sky, it's a tapestry of temperature variations, some patches slightly warmer, others cooler, like the walls of a fingerprint or the subtle ridges of a dried riverbed. These fluctuations aren't random. They're echoes of quantum ripples from the universe's first trillionth of a second, stretched to cosmic scales by inflation, the explosive expansion that shaped everything. The Planck satellite, launched in 2009, mapped these variations with stunning precision, revealing a pattern so intricate it looks almost woven. Each hotspot, each cold streak tells a story. The warmer regions, those are the seeds of future galaxies, where matter clumped a little denser, pulled by gravity toward its destiny. The cooler spots, voids where less matter pooled, leaving stretches of emptiness that would one day yawn between galaxy clusters. It's as if we're staring at the universe's blueprint, a coded message from the moment light first broke free from the fog of primordial plasma. And just as tree rings can tell us about droughts and storms in Earth's past, these cosmic ripples hint at the forces that shaped the infant cosmos, dark matter's invisible scaffolding, dark energy's latent push, even the possible existence of other dimensions crumpled too small for us to see. But here's what's truly humbling. The cosmic microwave background isn't just a relic. It's still here, still whispering, the static on an old analog TV. About 1% of that noise is from these ancient photons, hitting the antenna after traveling for over 13 billion years. We're literally bathing in the Big Bang's afterglow, a fossilized echo that permeates every cubic inch of space. Some scientists have even translated its fluctuations into sound, a deep, resonant drone punctuated by peaks and dips like the universe's first lullaby. Which raises a tantalizing question. If these patterns are the universe's birth cry, could there be others? Some theories suggest our cosmos might be one bubble in a frothing multiverse, each with its own unique microwave background, its own fingerprint. Inflation, the process that smoothed and stretched our early universe, could still be happening elsewhere, spawning new cosmic bubbles beyond our horizon. The Planck data holds subtle anomalies, unexpectedly large cold spots, curious alignments that some researchers speculate could be bruises from collisions with neighboring universes. It's a radical idea, but then again, so was the Big Bang once. The cosmic microwave background doesn't just connect us to the past, it might be the first clue to a reality far vaster than we ever dreamed. What if our universe isn't the only one, but just one bubble in an endless cosmic foam? This is the startling premise of bubble universe theory, where each bubble floats in a vast multiverse, its own self-contained cosmos with unique physical laws. Picture a boiling pot of water. Steam rises, forming ephemeral pockets of air that pop and reform. Now imagine those bubbles are entire universes, each born from the same seething quantum foam, but cooling into wildly different realities. Some might have gravity 1,000 times stronger, rendering stars unstable. Others could lack electromagnetism entirely, leaving atoms unable to bond. And a rare few, like ours, might strike the delicate balance needed for galaxies, planets, and life to emerge. This idea isn't as far-fetched as it sounds. Just as Darwin's finches evolved specialized beaks to exploit different niches in the Galapagos, universes in the multiverse could adapt through random variations in their fundamental constants. A slight tweak to the strength of the nuclear force, for instance, might make carbon, the backbone of life, impossible to form. Another might prevent atoms from clustering into molecules. Our universe's seemingly perfect fine-tuning, then, isn't a miracle, it's a statistical inevitability in an infinite sea of possibilities. We don't live in a special cosmos. We live in one of the few where conditions allow us to exist at all. Physicist Max Tegmark takes this even further with his mathematical universe hypothesis. If reality is fundamentally mathematical, he argues, then every possible structure describable by equations must exist somewhere. Not just variations of our physics, but entirely alien dimensions where time loops in knots or space has 11 layers. In this view, the multiverse isn't just a collection of bubbles, it's an infinite fractal of realities, each governed by its own self-consistent logic. Some might resemble ours with minor twists, like a universe where light travels slower. Others could be so bizarre that human language lacks the words to describe them. Which raises a haunting question: could alternate realities branch like tree limbs, splitting with every quantum decision? The many worlds interpretation of quantum mechanics suggests just that. Every time a particle has a choice to spin left or right, to decay or not, the universe forks, creating parallel timelines where each outcome plays out. In one reality, you turned left at the intersection. In another, you went right, setting off a cascade of diverging futures. This isn't science fiction. It's a serious, if unproven, attempt to explain quantum weirdness, where particles seem to exist in multiple states until observed. Yet for all its grandeur, the multiverse idea brings us back to a profound irony. However many universes exist, ours remains the only one we know for certain harbors life. Its constants are so precisely balanced that even slight changes would render it sterile. The cosmological constant, which governs dark energy's push, is fine-tuned to 1 part in 10 to the power of 120, a number so incomprehensibly precise it's like hitting a bullseye on a dartboard the size of the observable universe. Whether this fine-tuning points to a deeper principle, a cosmic accident, or something beyond our current understanding, one thing is clear: our universe, whether alone or part of an infinite ensemble, is a place of astonishing harmony, and we're here to bear witness. The universe operates on a razor's edge of precision, so fine-tuned that even the slightest shift in its fundamental constants would render life impossible. Take gravity, for example. If the force binding matter together were just a fraction stronger, stars would burn their fuel too quickly, collapsing into black holes before planets could form. Too weak, and matter would never coalesce into galaxies at all. It's as if the cosmos calibrated its settings with life in mind, a phenomenon scientists call the Goldilocks principle. Earth itself is a perfect illustration, nestled in the habitable zone around our sun, where temperatures are just right for liquid water, not so close that oceans boil away, not so far that they freeze solid. But this delicate balance isn't just about location. Jupiter, with its chaotic storms and swirling gases, plays an unexpected role as Earth's cosmic bodyguard. Its massive gravity deflects asteroids and comets that might otherwise pummel our planet, clearing the stage for life to flourish undisturbed. Brandon Carter's anthropic principle offers a provocative lens for this fine-tuning. In its simplest form, it suggests that the universe's constants must allow for observers like us, because if they didn't, we wouldn't be here to ponder them. Some argue this is mere coincidence, a statistical fluke in an infinite multiverse where every possible configuration exists. Others see it as evidence of something deeper, a hint that consciousness isn't just a byproduct of the universe, but perhaps a fundamental part of its architecture. After all, the same laws that govern star formation also shape neural networks in our brains, as if the cosmos is wired to not only create life, but to eventually understand itself through us. Consider the cosmological constant, which dictates the rate of the universe's expansion. If this value were even slightly larger, galaxies would have been ripped apart before they could form. Slightly smaller, and the cosmos would have collapsed back on itself eons ago. The odds of hitting this perfect equilibrium by chance are astronomically low, like rolling a die and landing on the same number a trillion times in a row. Yet here we are, in a universe where matter organizes into galaxies, stars forge heavy elements, and planets provide safe harbor for molecules to assemble into thinking, feeling beings. This fine-tuning extends beyond physics to chemistry. Carbon, the backbone of life, exists in abundance because of a freakish resonance in the nuclear reactions inside stars. Without this precise energy level, carbon atoms would be vanishingly rare and life as we know it impossible. Even water, with its unique ability to dissolve nutrients and regulate temperature, owes its properties to the exact shape of its molecule, a shape dictated by the electromagnetic force's precise strength. So what does this mean for our place in the cosmos? If the universe is a symphony, then life isn't just a random note, it's the melody the whole composition was built around. Whether by chance, necessity, or design, the constants of nature align with eerie precision to make our existence possible. And that raises a question as profound as any in science. Is the universe fine-tuned for life, or is life fine-tuned to perceive the universe's harmony? The answer, whatever it may be, suggests that we're not just bystanders in the grand scheme of things, we're part of the equation itself. What if consciousness isn't something the universe produces, but something it's made of? This is the radical proposition of Panpsychism, the idea that even the smallest particles of matter possess some rudimentary form of awareness. Not human-like thoughts, of course, but a flicker of subjective experience, a proto-consciousness as fundamental to reality as mass or charge. Picture an electron. We know it spins, carries energy, responds to forces. Could it also harbor the faintest whisper of feeling? If that sounds outlandish, consider this. The human brain, with its 86 billion neurons, generates the rich tapestry of our inner lives. Yet those neurons are built from atoms, which themselves arose from quantum fields humming with potential. Where exactly does consciousness emerge in that chain? The parallels between neural networks and cosmic structures make this question even more tantalizing. A single neuron with its branching dendrites looks eerily similar to a galaxy's spiral arms. Zoom out further, and galaxy clusters resemble neural networks on a cosmic scale, with filaments of dark matter acting like synaptic connections between celestial cells. Both systems process information, one through electrical impulses, the other through gravity's invisible signals. Both evolve over time, forming ever more complex structures. And both, in their own way, seem to encode and transmit something fundamental about the nature of reality. Carl Sagan captured this beautifully when he wrote, "We are a way for the cosmos to know itself, a poetic truth that might hold scientific weight." If consciousness is woven into the fabric of space-time, then our thoughts aren't just byproducts of biology, they're the universe waking up to its own existence. This raises a wild but wondrous possibility. Could stars, in some ineffable way, dream? We know they pulse with magnetic fields, vibrate with acoustic waves, even generate complex chemistry in their cores. A supernova's death throws forth the very elements that make up our bodies: carbon, oxygen, iron, scattering them like cosmic seeds. If panpsychism holds, then these processes might carry more than just physical significance. They could be part of a vast, slow momentum mind, a form of awareness operating on timescales we can barely fathom. The physicist Freeman Dyson once mused that the universe might possess a kind of mental dimension, with our own consciousness as a localized spark within a grander, more diffuse sentience. Now shift the lens to human creativity, the way a composer channels emotion into melody or a painter translates vision into color. These acts of creation mirror the universe's own generative power. A star's fusion and a poet's metaphor both rearrange raw materials into something new, whether it's helium from hydrogen or meaning from words. The difference is scale and speed, not essence. When we invent, we're tapping into the same creative current that spun galaxies from quantum foam, a current that might not just shape reality, but in some profound sense know it. The artist's brushstroke and the supernova's light could be two expressions of one universal impulse, to bring the unseen into being, and in doing so, to be seen. In 1911, Wassily Kandinsky stood before a canvas and painted something no one had ever seen before, an explosion of color and form with no recognizable figures, just swirling shapes that seemed to vibrate with energy. He called it Composition 4, and to the untrained eye, it might have looked like chaos, but Kandinsky insisted he was painting music, translating the harmonies of the cosmos into visual form. Decades later, astronomers would capture images of distant nebulae, their tendrils of gas curling in radiant hues, and the resemblance was uncanny. It's as if Kandinsky's brush tapped into some universal rhythm, a hidden grammar of spirals and splashes that the cosmos itself uses to paint the sky. Vincent van Gogh's Starry Night takes this cosmic echo even further. His turbulent sky isn't just a fantasy. Modern fluid dynamics simulations reveal that the swirling patterns in his painting match the behavior of plasma under magnetic fields, the same forces that shape solar flares and auroras. Van Gogh, who once wrote about feeling terrified by the night's infinite vastness, might have been channeling more than emotion. His thick, rhythmic brushstrokes mirror the mathematical turbulence found in nature, from cloud vortices to the spiral arms of galaxies. Scientists analyzing the painting's luminance found it follows the same statistical patterns as natural turbulence, suggesting the artist's eye, consciously or not, captured a fundamental truth about how energy moves through the universe. Sacred geometry takes this connection even deeper. Walk into the nave of Chartres Cathedral, and your gaze is drawn upward to the vaulted ceilings, where ribs of stone intersect in perfect symmetry. These Gothic masterpieces were designed using the Golden Ratio and Fibonacci sequences, the same proportions found in sunflower seeds and hurricane spirals. The rose windows, with their intricate petals of stained glass, echo the fractal branching of frost crystals and the radial symmetry of distant planetary nebulae. Medieval architects believed these shapes held divine significance, a language of God written into the fabric of creation. Today, we might say they were intuiting the universe's favorite blueprints, patterns so efficient, so universal, that they emerge in sacred spaces and supernova alike. This raises a provocative thought. If art mirrors cosmic patterns, is creativity itself a kind of resonance, a way for the human mind to sync with the deeper algorithms of nature? Modern tools are now amplifying this connection. Algorithms trained on astronomical data generate art that blurs the line between simulation and abstraction, while AI models analyzing Van Gogh's brushstrokes can predict fluid dynamics with startling accuracy. Even the James Webb Space Telescope's images, processed by scientists into rainbow-hued masterpieces, owe their palette to choices that feel almost artistic, highlighting methane in blues and dust in gold, as if the cosmos were a canvas waiting for interpretation. Perhaps art isn't just humanity's attempt to mimic the cosmos. It might be proof that we're wired to recognize and recreate the patterns that built the universe. From Kandinsky's spirals to cathedral arches, we've been speaking the cosmos's visual language all along. And now, with technology as our collaborator, we're not just echoing the universe. We're starting to converse with it. In a quiet lab at the University of California, an artificial intelligence stared at the night sky, not through a telescope, but through petabytes of galaxy maps, learning to spot patterns no human eye could detect. Within weeks, it had discovered something astonishing. Thousands of previously unnoticed dwarf galaxies hidden in the noise of deep space surveys. These tiny cosmic structures, overlooked by astronomers for decades, turned out to be crucial pieces in the puzzle of dark matter's distribution. This isn't science fiction, it's the cutting edge of machine learning, where algorithms trained on cosmic data are rewriting our understanding of the universe's architecture. The same technology that recommends your next video is now decoding the universe's deepest secrets. Take protein folding, a problem so complex it stumped scientists for 50 years. In 2020, DeepMind's AlphaFold cracked it, predicting protein structures with near-perfect accuracy by recognizing patterns in molecular data. Strikingly, the way these neural networks learn mirrors nature's own solutions. The branching pathways of a trained AI's decision-making process look eerily similar to the mycelium networks beneath a forest floor, thread-like connections strengthening with each new piece of information, whether it's an amino acid sequence or a fungal nutrient signal. Both systems thrive on feedback loops, adapting their wiring to optimize efficiency in environments brimming with chaotic data. Even the search for extraterrestrial intelligence is getting an AI upgrade. SETI Breakthrough Listen project now uses machine learning to sift through radio telescope signals, filtering out earthly interference to spot potential alien transmissions. Traditional methods searched for repetitive, narrow-band signals like a cosmic SOS, but AI can detect more nuanced patterns, irregular pulses that might be navigation beacons, or compressed data streams resembling error-correcting codes. It's like teaching a machine to recognize not just a shout in the dark, but the rhythm of a whispered conversation. This raises a profound possibility. If AI can decode protein folds and galaxy clusters, could it one day listen to the universe itself? Astronomers are already translating gravitational waves into audible sound, letting us hear black hole collisions. AI might go further, identifying harmonic resonances in pulsar signals or quantum fluctuations that hint at deeper physical laws. Some theorists speculate that advanced neural networks could uncover mathematical constants embedded in cosmic background radiation, a numerical signature left by the universe's birth. Yet for all its sophistication, this approach echoes ancient traditions. Indigenous cultures from the Quechua to the Aboriginal Australians have long read the stars as a living text, interpreting celestial patterns as stories, calendars, and moral guides. The Dogon people of Mali knew of Sirius's invisible companion star centuries before telescopes confirmed it, their knowledge preserved through oral astronomy. Perhaps AI, in its relentless pattern-seeking, isn't inventing a new way to understand the cosmos, but rediscovering an old one where observation and intuition merge into a deeper kind of listening. The universe has always been speaking. The question is whether we're finally learning its language. Long before telescopes or supercomputers, ancient cultures mapped the heavens with nothing but observation and intuition, and their celestial stories often held truths modern science is only now uncovering. Take the Maya, who tracked Venus with such precision that their calendar predicted its 8-year cycle of morning and evening appearances within a margin of just 2 hours. They saw this planet not as a random dot of light, but as a celestial dancer locked in rhythm with Earth and the Sun, a gravitational waltz we now call orbital resonance. Today, astronomers confirm what Mayan priests recorded on bark paper codices. Venus's 5 synodic cycles align almost perfectly with 8 Earth years, a harmony so precise it shapes the planet's climate and geology. The Maya called it the Great Return, a sacred interval governing ceremonies and harvests. Science calls it gravity's invisible hand, orchestrating planetary motion through mathematical ratios, yet both perspectives point to the same cosmic choreography. Half a world away, Hindu sages described time not as a straight line but as an endless wheel of creation and destruction. Their texts speak of universes breathing in and out over epochs called kalpas, each lasting billions of years, with new worlds rising from the ashes of the old. For centuries, this seemed like poetic metaphor until modern physics introduced the cyclic universe model, where the Big Bang might not be a singular beginning but one pulse in an infinite series. Theorists like Roger Penrose propose that black holes from a previous universe could leave imprints in our cosmic microwave background, like echoes of a forgotten age. The math behind these bouncing cosmologies mirrors Hindu descriptions of Brahman's exhalation, the expanding universe, and inhalation, the cosmic collapse, suggesting ancient seers may have glimpsed a truth it took us millennia to quantify with equations. Meanwhile, Polynesian navigators crossed thousands of miles of open ocean by reading patterns modern science would later recognize as fractal. Maori sailors memorized the way waves interacted with distant islands, noting how swells bent around landmasses in repeating, scaled-down versions of larger currents. They called these ripple signatures wakaria, a navigation tool as precise as any GPS. Today, fluid dynamics confirms their wisdom. Ocean waves propagate in fractal hierarchies, with small eddies mimicking the behavior of vast currents. The Maori didn't need the word fractal to understand its logic. Their survival depended on seeing the ocean as a living, self-similar map. What unites these traditions isn't just accuracy, it's a way of knowing that blends observation with reverence. Where modern science dissects the universe into equations, indigenous cosmologies often perceived it as a web of relationships, where celestial bodies weren't isolated objects but participants in a grand dialogue. The Dogon people of Mali, for instance, knew of Sirius B, a white dwarf star invisible to the naked eye centuries before telescopes revealed it. Their oral astronomy described it as Potolo, a dense, heavy star orbiting Sirius every 50 years, a fact confirmed by astrophysics in the 19th century. Whether through star lore or spectroscopy, humanity has always sought the same truths, just through different lenses. This convergence raises a humbling question. Could the oldest stories hold keys to the newest frontiers? Quantum physicists grappling with entanglements, spooky action, might find kinship in Aboriginal Australian Dreamtime, where distant locations are spiritually connected through songlines. Astronomers probing dark matter's web could learn from Navajo weavers, whose rugs depict cosmic symmetries resembling supercomputer simulations of galaxy filaments. Science and tradition aren't rivals, their fellow travelers on a journey to decode the universe's patterns. And as we peer deeper into space with our machines, we might rediscover what the ancients always knew. The cosmos speaks in rhythms, and to understand it, we must learn to listen. The James Webb Space Telescope has gifted us more than breathtaking images. It's handed us a cosmic decoder ring, revealing how the universe builds galaxies in stages so precise they resemble the branching of a fractal tree. Stare into the heart of NGC 626, a newborn galaxy captured by Webb's infrared gaze, and you'll see something astonishing. Delicate tendrils of gas spiraling inward, their paths mirroring the veins of a maple leaf or the tributaries of a river delta. These aren't just pretty shapes, they're snapshots of gravity's patient work, sculpting chaos into structure one fractal iteration at a time. Webb's vision pierces through dust clouds that once hid these formative moments, showing us how galaxies mature in cycles, their arms unfurling like fern fronds reaching for sunlight. Compare this to Hubble's iconic Pillars of Creation, where towering columns of interstellar gas glow with the same dendritic intricacy as frost spreading across a windowpane. The resemblance isn't superficial. Both systems, whether stellar nurseries or ice crystals, are shaped by the universal language of fluid dynamics, where turbulence and pressure conspire to create self-similar forms. Hubble showed us the beauty. Webb reveals the blueprint, capturing galaxies in their embryonic state with such clarity that we can trace the fractal fingerprints of their growth. Yet these telescopes are more than just cameras, they're time machines. Every photon Webb collects has traveled billions of years, carrying whispers from an era when the universe was assembling its first large-scale structures. The data streaming back isn't just reshaping astronomy, it's rewriting our understanding of cosmic interconnectedness. Algorithms now map the distribution of dark matter by analyzing the subtle warping of starlight, a technique called gravitational lensing that feels almost like reading the universe's hidden handwriting. Machine learning sifts through petabytes of telescopic data, spotting patterns even the most trained eyes might miss, drawing lines between quasar emissions and the neural networks of the human brain. This convergence of technology and cosmic imagery invites a profound shift in perspective. Indigenous navigators once charted oceans by reading wave patterns. Today, we navigate the cosmos by decoding gravitational ripples and quantum fluctuations. The philosophy isn't new, only the scale has changed. Hindu texts described Indra's net, a metaphor for reality where every jewel reflects all others, infinitely interconnected. Now, Webb's images of galaxy clusters lensing distant starlight offer a scientific echo of that ancient vision. Each point of light bending and warping in response to the mass of everything around it, a celestial dance of mutual influence. Perhaps the most humbling revelation isn't how advanced our tools have become, but how deeply they reaffirm an old truth that the universe repeats its favorite patterns like a composer revisiting a theme, from the spin of electrons to the spin of galaxies. The pillars of creation and the branching of neurons, the spiral of a hurricane and the spiral of a protoplanetary disk, they're all verses in the same cosmic poem. And with every technological leap, we're not just observing the universe's artistry, we're learning to read its starlit stanzas aloud. The universe hums with a secret, that every atom, every galaxy, every conscious thought might be stitched together by invisible threads, binding the quantum to the cosmic in a web of staggering unity. Consider this: when two particles become entangled, a change in one instantly ripples through the other, whether they're inches apart or light years away. This isn't just physics, it's a whisper that separateness might be an illusion. As the Zen teacher Thich Nhat Hanh once reflected, we are made of stardust, not as poetry, but as literal truth. The iron in your blood, the calcium in your bones, were forged in the hearts of long-dead stars, scattered across the cosmos in supernova explosions billions of years ago. You aren't just in the universe, you are the universe, rearranged into a form that can ponder its own existence. This interconnectedness plays out in cycles both vast and intimate. The water you drank today has circled the globe through rivers, clouds, and rain for eons, the same molecules that once quenched the thirst of dinosaurs or rippled in primordial tides. On a grander scale, galaxies recycle themselves through cosmic epochs, their stars birthing the elements that will one day form new worlds. Even time, which feels so linear to us, might be more like a spiral with patterns recurring across scales. Indigenous traditions have long understood this. The Maori see ancestors in the stars. The Lakota speak of the sacred hoop, where endings are beginnings. Modern physics echoes this wisdom with theories of cyclic universes and quantum loops suggesting that nothing truly ends, it transforms. So what does this mean for you right now? Start with your breath. Each inhale pulls in oxygen atoms released by distant forests or oceanic plankton, while every exhale joins the atmosphere's ancient dance. The screen you're staring at, its silicon chips trace their lineage to stardust, just like your own cells. This isn't just spiritual abstraction, it's biochemistry, astrophysics, and ecology converging into one startling realization: you're never truly alone. The boundaries between you and the world are porous, negotiated constantly through every touch, every glance, every shared moment. Perhaps that's the ultimate takeaway. When you feel disconnected from others, from purpose, from the cosmos, remember the stardust in your veins, the entangled particles in your devices, the water molecules that have sung inside thunderstorms and glaciers long before you were born. The universe isn't something out there. It's the air in your lungs, the light in your eyes, the synapses firing as you make sense of these words. And if that's true, then every act of kindness, every spark of curiosity, every step toward healing our planet isn't just a choice. It's the universe tending to itself through you. Next time stress weighs you down, try this. Trace the veins of a leaf with your fingertip, following each branching path as it splits into smaller and smaller tributaries. There's a reason this simple act feels grounding. Fractals, those infinitely repeating patterns found in ferns, river deltas, and even our own lungs, have a unique effect on the human mind. Studies show that exposure to fractal shapes, whether in nature or art, lowers stress levels by up to 60%, likely because our brains evolved surrounded by these patterns. The rhythmic repetition soothes our neural circuits, like a lullaby written into the fabric of the world. Neuroscientists call it fractal fluency, our innate ability to process these shapes effortlessly, as if recognizing an old friend. For a deeper immersion, step outside. A walk through a forest isn't just exercise, it's a masterclass in cosmic geometry. Notice how tree branches mirror lightning bolts, how roots sprawl like galactic filaments, how the dappled sunlight filtering through leaves creates fractal shadows on the ground. Indigenous cultures have long understood this connection. The Maori concept of Wakapapa describes all life as an interconnected web, where mountains, rivers, and stars share the same ancestral patterns. Modern science echoes this wisdom. The same mathematical algorithms that govern how trees branch also shape how galaxies cluster. When you walk with this awareness, every oak and pine becomes a living bridge between the microscopic and the cosmic. Creativity, too, thrives when we sync with these universal rhythms. Composer John Cage famously drew inspiration from the I Ching's randomness, while architect Frank Lloyd Wright embedded the golden ratio into his designs, letting cosmic proportions guide human spaces. Try this exercise: sketch a spiral, the same curve found in seashells and hurricanes, then let it guide a poem or melody. Or map your daily routine to celestial cycles. Wake with the sun's rise, tackle complex tasks when your mental energy peaks like a star at its brightest, and wind down as the light fades. Your productivity might just align with the universe's pulse, which brings us to storytelling, the universe's oldest art form. Long before humans carved symbols into cave walls, the cosmos was spinning narratives through starlight. Supernova seeded space with the ingredients for planets. Comets carried water to young Earth. Gravitational waves now ripple through space-time like plot twists written in invisible ink. Every culture that's gazed upward has woven these events into myth, from the Navajo's coyote scattering stars to the Greek titans warring in the heavens. Science, at its heart, is simply the latest chapter in this tradition, decoding the universe's epic through equations rather than allegory. So the next time you feel overwhelmed, remember, you're not just a speck in the chaos. You're a participant in a story billions of years in the making. Your breath synced to the same rhythms that spin galaxies and shape shorelines. Whether through meditation, observation, or creation, you're tapping into a dialogue that began with the first light of the cosmos and continues every time you pause to trace a leaf's veins or marvel at the night sky. Every great culture has its creation myth, stories of chaos giving way to order, of gods shaping the world from darkness. The ancient Greeks spoke of Gaia emerging from the void. The Maori told of Ranginui and Papatuanuku, the Sky Father and Earth Mother, locked in an embrace until their children pried them apart to let light in. These tales weren't just entertainment, they were frameworks for understanding a vast, mysterious universe. Today, we have our own epic cosmology, and it's stranger than any myth. Instead of gods, our heroes are pioneers like Vera Rubin, who stared into the abyss of galactic rotations and found them spinning too fast, their stars clinging to orbits that defied gravity's rules. The twist, an invisible protagonist, dark matter, whose gravitational pull holds the universe together like unseen hands gripping a celestial marionette. This cosmic narrative has all the elements of classic mythology. There's the call to adventure, Hubble's revelation that the universe is expanding, the ordeal, the decades-long struggle to reconcile quantum mechanics with gravity. The revelation, the discovery that ordinary matter makes up less than 5% of existence, with dark matter and dark energy as the shadowy figures pulling the strings. Even the archetypes align. Einstein plays the wise sage, his equations hinting at truths he himself doubted. Jocelyn Bell Burnell is the underdog, her pulsar discovery initially dismissed before revolutionizing astrophysics. And the latest chapter, the Anthropocene, where humanity steps onto the stage not just as observers, but as actors shaping the planet's fate, a role as daunting as any hero's quest. The ancients saw constellations as divine figures. We map the cosmic web, a labyrinth of dark matter filaments where galaxies cluster like cities along invisible highways. Both are attempts to impose narrative on chaos, to find meaning in the patterns. But here's where our story diverges. Mythologies often ended with tidy resolutions: the storm god subdued, the harvest secured. Our cosmic tale has no final act. Dark energies accelerating expansion might lead to a cold, lonely fade out, or a cyclical rebirth we can't yet foresee. And unlike the heroes of legend, we're both audience and authors, our choices etching lines into the plot. The carbon in our atmosphere, the satellites in our orbit, these aren't just footnotes. Their plot twists in a saga written across 13 billion years. So where does that leave us? Perhaps as the universe's first mirrors, creatures complex enough to reflect on its grandeur. A star knows only fusion, a black hole only gravity. But we trace the Fibonacci sequence in sunflower seeds and supernova alike, sensing a thread connecting quark to quasar. That's the real magic of this story, not just that we're in it, but that we can tell it. When a child points to the moon or a researcher models galaxy formation, they're adding verses to the oldest poem there is, one where every equation, every observation, every act of stewardship is a stanza in the universe's song of itself. Humanity stands at a crossroads between two visions of our place in the cosmos, one that sees Earth as a resource to exploit, and another that recognizes it as a fragile node in an ancient, interconnected web. The difference between these worldviews isn't just philosophical, it's written into the very patterns of the universe. Take the concept of circularity, for instance. Nature knows no landfills. A fallen oak becomes a nursery for fungi. its decay feeding new growth in an endless loop. Similarly, stars forge heavy elements in their cores and scatter them across space in supernova explosions, a galactic recycling program that's been running for billions of years. Modern sustainability efforts, from zero-waste cities to cradle-to-cradle manufacturing, aren't just ethical choices. They're alignments with a deeper cosmic logic, a recognition that linear systems make, waste are anomalies in a universe built on reciprocity. This wisdom isn't new. Indigenous cultures have long operated within this paradigm, viewing themselves not as owners of land but as participants in its cycles. The Maori principle of Kaishiakitanga, or guardianship, teaches that humans are stewards obligated to protect ecosystems for future generations. Compare this to the short-term extraction mindset that's driven deforestation and climate crises, and the contrast is stark. One sees the planet as a relative to nurture, the other as a commodity to exhaust. Astronomer Neil deGrasse Tyson frames this shift elegantly. The cosmic perspective shows Earth as a tiny, fragile oasis, a pale blue dot suspended in the void. It underscores our responsibility to preserve and cherish it, the only home we've ever known. That perspective isn't just poetic, it's survival. When astronauts describe the overview effect, the profound sense of unity and responsibility felt when viewing Earth from space, they're tapping into the same realization that indigenous cosmologies have honored for millennia. Borders and divisions are human inventions. From orbit, the atmosphere has no seams. Awe becomes the bridge between knowledge and action. Studies show that exposure to vast, humbling experiences, whether standing beneath a star-filled sky or witnessing time lapses of glacier retreat, triggers the brain's default mode network, the same region active during empathy and moral reasoning. It's as if the universe wired us to respond to grandeur with reverence and care. This neural alchemy might explain why cultures that celebrated celestial events, from the solstice alignments at Stonehenge to the star maps of the Polynesians, often developed sophisticated conservation practices. They saw their fates as intertwined with cosmic rhythms. Now, imagine applying that lens to modern challenges. Circular economies modeled on fungal networks could revolutionize industries. Urban planning inspired by termite mounds self-cooling, self-ventilating might slash energy use. Even space exploration, often framed as an escape hatch for a ruined Earth, could refocus on planetary stewardship, using asteroid mining not for unchecked consumption, but to reduce pressure on terrestrial resources. The cosmos doesn't just offer patterns to admire, it provides blueprints for balance. When we align with them, we're not just solving problems, we're joining a 13 billion-year-old conversation about how complex systems endure. And in that dialogue, every sustainable choice, from composting to coral restoration, becomes a stitch in the tapestry of cosmic reciprocity. There's a reason we feel small under a starry sky, yet somehow more connected. A paradox science is only beginning to unravel. Studies at Stanford and UC Berkeley reveal that awe, that spine-tingling sense of wonder in the face of vastness, doesn't just lift our spirits, it rewires our brains. Participants who spent time staring at towering redwoods or watching Hubble's deep field images showed increased activity in the vagus nerve, the neural highway linked to empathy and social bonding. It's as if the universe designed awe to be a reset button for the human soul, dissolving the illusion of separateness that fuels so much conflict. Japanese Shinrin Yoku, or forest bathing, prescribes mindful immersion in nature to lower cortisol levels. But stargazing might be its cosmic counterpart, where dappled sunlight through leaves becomes starlight through telescopes, both reminding us we're part of something incomprehensibly larger. I'll never forget my first night in Chile's Atacama Desert, where the Milky Way arched overhead like a bridge of crushed diamonds. As my eyes adjusted, the sky didn't just feel above me, it felt within me, as if the boundary between observer and cosmos had blurred. That moment of vertigo wasn't fear, it was recognition. Astronomer Carl Sagan described this sensation as the universe becoming conscious of itself, but poets and pilgrims have felt it for millennia. The builders of Newgrange aligned their tombs to winter solstice sunrise. The Navajo charted their ceremonies by the Pleiades. These weren't just calendars, they were technologies of awe, rituals to realign human perspective with cosmic rhythms. Now imagine harnessing that power globally. In a divided world, shared awe could be the ultimate diplomat. When Apollo astronauts broadcast images of Earth rising over the lunar horizon, it sparked the environmental movement not through policy but through perspective. That fragile blue marble, suspended in blackness, made borders absurd and kinship obvious. Today, virtual reality lets anyone stand on Mars' ridges or float through Saturn's rings, offering glimpses of what philosopher Frank White calls the overview effect without leaving home. Could regular doses of cosmic perspective soften ideological trenches? Early research suggests yes. Groups exposed to awe-inspiring nature footage before negotiations reached compromises 20% faster, their brains shifting from defensive to exploratory modes. This isn't just about feeling good, it's about survival. Awe stretches our mental timelines, making us prioritize long-term stewardship over short-term gain. After viewing images of nebulae, volunteers in one study donated 30% more to climate charities, as if the cosmos had whispered, "You're part of this story, act like it." Indigenous cosmologies have always known this truth. The Kogi people of Colombia call themselves elder brothers, tasked with maintaining Earth's balance, while Western science now quantifies how wonder dissolves the ego's walls. Perhaps uniting humanity doesn't require a common enemy, but a common marvel. The shared realization that we're temporary custodians of a tiny world, adrift in a grand design far beyond our full comprehension. As we prepare to synthesize these threads, consider this final thought. Awe doesn't diminish us, it contextualizes us. The same laws that spin galaxies also animate our synapses. The same stardust that forged quasars now fuels our curiosity. In lifting our gaze to the heavens, we're not escaping Earth, we're rediscovering it, fresh and fragile, as if seeing it for the